So hello everyone, my name is David Hicks, and in this particular AFLOW session I'm going to be talking about the AFLOW Encyclopedia of Crystallographic Prototypes that we've been developing over the past few years. And in particular I want to highlight this idea of using this encyclopedia to automatically generate new materials for high throughput materials discovery. And so I'm briefly going to highlight some of the online functionality as we said, but there is functionality to do this via the command line, and we also have a Python module as well to help you interface and create these structures. Okay, so the first thing that we need to do is find these prototypes. So there are many different catalogs throughout the literature. In particular, you may be familiar with Pearson's Handbook, the Strukturbericht series. Please forgive my German pronunciation. And then there's also things like the American Mineralogist Crystal Structure Database. And so these are very useful resources. However, many of them, in particular, these top three here, they're printed, and so you can't easily extract them to make them into geometry files or coordinate models. And so there are some computational hurdles with this. And so that's the first one. And the second one is a lot of these typically have arbitrary designations. So for example, you might have the rock salt structure here, and sometimes it's referred to as NaCl, so the sodium chloride, or maybe magnesium oxide. And they have the same geometry, same atomic positions, but they may be referenced differently depending on what material they chose as that representative. In addition, there's also this Strukturbericht designation. And so for instance, for rock salt, it's B1. However, this doesn't really tell you much about what the structure actually looks like. And so again, this was a useful designation early on, but then as you explore more complicated materials, unfortunately this designation was dropped and wasn't really kept up. And so one thing that we wanted to keep in mind when designing this encyclopedia was we wanted to overcome this idea of arbitrary designations and have an intuitive method to reference these structures. In addition, a lot of these rely on the user having a base knowledge of crystallography. So for example, a lot of these resources might give you the crystal having space group 216, for instance, and then it may give you the Wyckoff position for the silver atom, and then this sequence of characters here. And so you would need to know that, this is the Wyckoff position, and this is the multiplicity. So the number of atoms in the conventional cell, the letter designation, and then the representative coordinate. And then you would need to go to a resource such as the International Tables for Crystallography to actually expand out this position into its 4 coordinates. And so this is based on the symmetry of this structure. And so again, this is a hurdle if you want to do this automatically to transform this from this representation of the prototype and actually generate a geometry file for this. And so this is what we wanted to overcome. And so this is known as the AFLOW Crystallographic Prototype Encyclopedia. And so AFLOW contains built-in structural prototypes. So for example, the Heusler structure, anti-Heusler, half-Heusler, and many common structure types that you're probably familiar with. And so the idea behind this idea of prototypes, and I think it was mentioned maybe in a few talks earlier, is that we would take this crystallographic prototype and we would go to the periodic table and decorate it with different elements and create new hypothetical materials. And so this method is very useful for automatic materials designs. And so currently we have 600 prototypes that are online, which I'm going to show in a little bit. And so again, this is the AFLOW Prototype Encyclopedia. And this was actually originally an effort by Professor Mike Mell when he was at the Naval Research Laboratory. Unfortunately, the prototype library was taken down and for redesign, and it wasn't put back up. But we recently have joined forces with Professor Mell and brought back the encyclopedia, and we've also been increasing the number of prototype entries. And so the content of this encyclopedia, so there's currently 590 prototypes, and each prototype will give you a standard label, which I'll discuss in the next slide. There's also the historic label, so whether it was rock salt, or maybe the structure designation, similar compounds that exhibit this structure, and then some symmetry information as well. And in addition, probably the most important aspect of the encyclopedia is that it's coupled with the AFLOW software, so that way we can automatically generate these prototypes for materials discovery. And I'll go through that shortly. And so there's a few parts or volumes to this encyclopedia. So part 1 contained 288. Part 2, we added 302, and that gives us the 590 prototypes. And there's at least one representative from each of the 230 space groups. So we're starting to span crystallographic space with these prototypes. And part 3, we've actually been working on the last few months, and we're very close to having this available. And this will essentially double the encyclopedia that's here now. And so I mentioned that we wanted to come up with a standard designation that actually tells you a little bit what the structure or prototype looks like. And so, for example, we have the Quartzite prototype. And so we came up with this AFLOW label, and it's this string separated by underscores here. And so you can see, if you just look at this, you can probably see that there's some symbols or characters that you may be familiar with. And so in this first field, this gives you the reduced stoichiometry of the prototype. The second field is the Pearson symbol. So this tells us that it's a hexagonal structure, hexagonal primitive, and there's 4 atoms in the conventional cell. This third field is the space group number, and the subsequent fields are the Wyckoff letters associated with each of those species. So for example, this B indicates that species A has this Wyckoff letter, and species B has also this Wyckoff letter. And so this isn't enough to describe the prototype, because there's some degrees of freedom that the structure can have even with this representation. And so here we specify what are called the AFLOW parameters, which are the degrees of freedom consistent with symmetry. So for example, based on the symmetry given by this label, we would need to specify the lattice parameter A, the ratio of C over A, and then there's the Wyckoff positions. The Z coordinates are variables, and so we need to specify these as well. All the other variables that you may be thinking of, B, lattice parameter B, or alpha, beta, gamma, are fixed based on this symmetry, so we don't need to specify them. And so what's useful with this actual designation is that you can tune these degrees of freedom. So for example, if we change the C over A ratio, we can actually kind of squeeze the cell in the Z direction. Or additionally, we can actually change the Z positions, and we can change the distances between the atoms. And so even though this is one prototype label, we can actually generate many different crystal prototypes by tuning these parameters. But it's nice because you can actually change the degrees of freedom, but preserve the underlying symmetry. So even if you change these, you're gonna have the same symmetry. And so this is a very powerful prototyping tool. And so, as I said, we're going to be focusing mostly on the online application. So actually, I'm going to go ahead and navigate there now. So feel free to follow along. And hopefully everyone can still see my screen. So go ahead and open a web browser, and we're going to go to aflow.org. So Marco's already shown us how to get there. And you should see the main page. And if you scroll down, there's the AFLOW applications that are online. And so again, we're going to be discussing some of these later on, but in particular, we're interested in the prototype encyclopedia. So go ahead and click on this, and it should take you to this main page. And I'm actually going to increase size a little bit. Hopefully that's a little better for everyone. And so this is the online interface. So there's currently, as I said, 590 prototypes that are available. And you can actually search the prototypes based on certain structural descriptors, such as the space group, Pearson symbol, the structurische designation, if it has it. And there's also a prototype index as well. And then at the bottom, we advertise whenever we add some new functionality or new prototypes. And so that's listed here. So I'll go ahead and just briefly go through some of the tabs just to see how you can navigate the prototypes. So if we go to the space group, at the top bar, you can see that the prototypes are organized by the different space group ranges, so triclinic, monoclinic, orthorhombic. And if we click on this, we can see that we list the prototypes that are in the particular space group categories, so space group 17 and so on and so forth. If you go back to the top, you can search by Pearson symbol. So again, they're grouped by triclinic, monoclinic, all the way down to cubic. And so if we click on this, then they're arranged by Pearson symbol. So in this case, CF4, CF8, and it goes all the way through the cubic Pearson symbols. And then, as I mentioned, there's also some prototypes that are designated by this Structurbericht designation. And so in this case, A, B, C, all the way down to, right now I think we have S, and part 3, we've actually completed the historical record of the Structurbericht designations. And so in part 3, this will be a complete set. And then you can also view by chemical symbol, so species. And then we also have this prototype index. So if you go here, this is a sortable table. And so you can actually sort by the prototype or the number of atoms, the number of species. And then let's say you want to define maybe all the perovskite structures that we have. So we can start to type perovs. Just do this. And you can see that, okay, it's shortened the table. And then we can see that we actually have 3 perovskite type structures. And again, you can arrange these. And then you can actually click on this to take you to the prototype page. So again, this is a useful tool to quickly navigate the prototypes online. And then additionally, if you're not very familiar with crystallography, or if you want to know some of the conventions that we use for the encyclopedia, you can go to Crystal Info. And so you can see how we define some of the crystal lattice systems. So for example, the orthorhombic crystal system, how we define the lattice vectors, and then what's the difference between simple orthorhombic and what space groups are in this lattice type, and then base set orthorhombic, and so on and so forth. Additionally, if you wanted to get some more information about the different space groups, we have a table of the different space group notations used throughout the encyclopedia. So the number, the orientation, so that's particularly useful for lower symmetry structures. So this is unique axis B for monoclinic systems, and then the different symbols. So Hermann-Maguin, Hall, the international symbol, and Schoenflies. And then last, I wanted to mention is that we also give a little bit of information on the enantiomorphic space groups. So essentially that are that form enantiomorphic pairs between the space groups. And so they're essentially mirror images of one another. And so we've listed them here. And the reason that I mentioned this is that it was actually quite difficult to find some of the different space group categories for the prototypes. And so we actually used mirror images of some of the space groups to actually fill in the rest of this space group or the encyclopedia. And so we give some information here. So let's actually navigate to a particular prototype page. So if you go to the search bar here, let's go type in corundum. It'll take us to the search page. Again, you can search, this is a basic search, but you can search on space group, Pearson symbol. And so let's go ahead and we search for corundum. Let's go ahead and click on this, and it will take us to the prototype page. And so for each prototype in the encyclopedia, we have a corresponding web page. So for the corundum structure. And so at the top of each page, we have a JMOL interface, so you can rotate the structure. We have some predefined directions, so you can rotate it along the A axis, the B axis, C axis. You can also load supercells, for instance. So if you want to see a 3 by 3 by 3, it'll generate this. You can also visualize the, let me scroll down. You can also visualize the structure in the primitive representation, the conventional representation, or you can actually see both superimposed on one another. So again, this is useful for seeing the differences between the conventional representation and primitive. You can also see the Wigner site cell, if you'd like to do this. So you can see what that looks like. And then if you're familiar with JML, you can actually open a JML console and actually play with the figure a little more. So if we scroll down, then we see that we have the prototype. So this is the particular compound that exhibits this structure. So Al2O3, the prototype label, the Strukturbericht designation, Pearson symbol, space group information. And then if you're working with the command line, this would actually be the command to actually generate this structure programmatically. And so you can see we would designate the label and then the parameters. And so again, these are the parameters that need to be specified for this structure. We also provide information on maybe some other compounds that exhibit this structure. Some interesting comments that maybe we found in the literature when we were investigating this prototype. And then we also indicate the primitive vectors, but you'll notice that they're in symbolic notation. So they're given with respect to A, B, C, alpha, beta, gamma. And so again, this is a useful representation because we can actually tune these degrees of freedom to generate a slightly different structure. And the same goes for the basis vectors. So these are the atomic positions in the primitive cell, and they're given with respect to the lattice, so the lattice coordinates or the Cartesian coordinates. Wyckoff positions, and then also the atom type. We give the references, so where we found the structure. And then there's also some geometry files that are already generated that you can download either the CIF or the PostCar. But the most important aspect is at the bottom of the page here, which is the prototype generator. And so this allows users to generate this particular prototype structure, specifying the degrees of freedom, whatever species you'd like on these positions, and then you can generate various geometry files. So for example, we've already defaulted the parameters here and the species. And so we support a variety of different formats. VASP, so you can see this will generate a VASP output file or geometry file. And this would be the corresponding AFLOW command to generate this structure if you're working with the command line. And so what's happening here is this website is actually interfacing with the AFLOW software to generate this structure. And so we can also print out a quantum espresso geometry file. If you work with FHI AIMS, we have the AIMS input file, abinit. There's also YCAR, which is essentially a VASP postcar, but we've represented it with respect to the Wyckoff positions. So for example, you can see that we've actually condensed it, the atom positions, into the representative Wyckoff position, and we give the multiplicity, the Wyckoff designation, letter designation, and then the site symmetry. And you can see this is space group 167 and space group setting 2. So in this case, it's the hexagonal setting. And so actually, one thing I want to mention is this is actually calling AFLOW symmetry module to perform the symmetry analysis of whatever structure is generated here. And so we're actually going to be using this in an exercise later on. Additionally, we have the CIF output and then ELK as well, if you're familiar with that. And then let's say you tune these degrees of freedom. Let's say instead of aluminum, we put iron. And we want to see what the structure looks like now. So we can hit refresh JML, and it'll take us back to the JML viewer. And now you can see we've decorated the prototype with iron and oxygen. And so this is essentially the idea or what's listed for each prototype Encyclopedia entry. So I guess, are there any questions on what the web interface looks like on generating these structures with the online prototype interface? If there is, feel free to post in the chat. And if not, I'm going to navigate back to the presentation. So let me pull that up. And so if people are interested, I've basically highlighted the prototype information on the slides. And if you'd like these slides, let us know, and these will be available on the AFLOW school page that Marco mentioned earlier. Okay, so are there any questions up to this point on the AFLOW prototypes? Okay, so it doesn't look like there's any questions. So now we're gonna go through some exercises just so you can familiarize yourself with the prototype encyclopedia. So this first exercise, again, where you're just gonna navigate to the web page, and then just to use the search functionality or familiarize yourself with it, go ahead and look up these structures and what are the AFLOW labels of these structures. So for example, I'll do the last one since people may not get to it. So we're gonna look for solvenite. So again, you can just go to the search banner at the top and type solvenite. And it should pull it up right away. You click on it, and then you should see the prototype entry page that I showed before for the structure, and then you can find the information here. So this is, again, this first exercise is just to kind of navigate the website. And then this next exercise is to use, to go to a particular prototype page. So it has this label. And so I would recommend looking up by space group or Pearson symbol. And what you'll do is you'll use whatever element and value of A parameter you'd like, but then go ahead and change the C over A values to first 0.5, second 0.612, and so on and so forth. And for each one, go ahead and calculate the space group. So to do this, you would click on the YCAR or the SIF button, which calls a symmetry in the AFLOW sim analysis under the hood. And this will tell you what the space group is. And so I want you to note any changes to the symmetry if there are any. So maybe I'll go ahead and give you maybe 5 minutes or so to go ahead and play with these exercises. If you have any questions or problems, feel free to post in the chat. Okay, so if everyone's on the prototype webpage, so yeah, this one was a little trickier to look up. So actually, let's go ahead and navigate. If you click on the encyclopedia icon, it'll take you back to this main page. And if you actually hit search, it'll take you to this other web page. And so let's actually type in, so we're looking for space group 166. And then if you look at the label, that's what we see. So space group 166, and the Pearson symbol is HR1. And so if we hit search, there may be a few that pop up. So this is a string search, so that's why you see 13 instead of all ones. But in this case, this is the structure we're looking at. So you can see, so it may have been also a little confusing because we also had this label here as well, and this is actually different degrees of freedom. But in this case, I think I said we were looking for beta polonium and structubric AI. So if we click on that, it'll take us to this page. And so if we go to the bottom of the page, the exercise said to go to the prototype generator. And so in this case, we want to, you can use any element or value of A that you'd like, but then change the C over A values to these, and for each one, calculate the space group. Okay, so I'm gonna put this at the bottom of my screen so we can kind of still see it. So let me, there we go. Okay, so what we wanna do is we're gonna change the C over A ratio to 0.5. And then to do the symmetry analysis, at least on this web page, you would hit the YCAR, or you could do SIF also, because what it's doing is it's calculating the symmetry on the fly in the background with AFLOW Sim. And so you can see in this case, if we look here, as I mentioned before, the space group number is given here. So if you're familiar with maybe the ABC car or YCAR, this gives you A, B, C, and then alpha, beta, gamma, then the space group and the setting. And so in this case, the space group is 166 with this value of C over A. If we change it to 0.612, hit the button again, we actually see that the symmetry changed. So we're actually in space group 229. So it's higher now. If we change it to 1.0, do the same thing. We're back to space group 166. If we go to 1.225, now we're at space group 221. So again, it changed 1.5, back to 166, and then 2.45. space group 225, so it changed again. And then the last one, 3.0, back to 166. So this kind of goes against what I said originally when I was introducing the prototypes, that if you change the degrees of freedom, you'll always preserve the underlying symmetry. You do preserve the symmetry, but you can also elevate it to an even higher symmetry. So in general, depending on how you tune the parameters, you always be in that symmetry category, or if maybe you tune it in such a way that you've transformed the cell into a higher symmetry. And so that is possible, and that's what we're seeing here. So are there any questions on that, or any remaining questions about the prototype encyclopedia? If so, feel free to post in the chat. I guess while I'm waiting for any other questions, one thing I wanted to mention is, again, we're only focusing on online functionality, but again, we want to have this automatic method of generating. And so you can generate these prototypes via the command line. So if you download AFLOW, you can actually type in these commands to basically do everything that I said automatically. And so again, it's the label and the parameters. And then there are different ways that you can create the different geometry files. And there's many different tools that you can use to actually play with these particular ways of creating geometry files. And there's also a Python interface as well to do this if you'd like to generate the structures. So if there aren't any questions, maybe, so somebody said they're having difficulty with the link. It states the site cannot be reached. Did you try the alternative link? Because I would recommend that, because sometimes you did try the, so aflowlib.duke.edu, search UI. That's a good recommendation from Corey, maybe clear the cache. So at least for me, it comes up. So yeah, it could be a caching issue. But yeah, if you're still having issues, feel free to write in the chat during some of the other talks. Okay, so maybe it worked. So if there aren't any other questions, I'll go ahead and pass it over. Or we might be taking or no, I think actually we're going to Corey's session next. So thank you, everyone. If you have any more questions, lingering questions, feel free to post in the chat. But if not, I'm going to go ahead and hand it over to Corey. So thank you, everyone.